Let's jump into today's material. Don't let me go past my squiggly line without moving my camera this time. Hate to lose that. So we're skipping the next chapter in the book, chapter 6. Chapter 6 is roughly about the difference between the name of an object and the object itself, the designator and the thing it designates. So I'll give you a quick example. If I were to write something like Bob has 3 letters, this is not true. Bob does not have 3 letters unless Bob is physically holding in his hand 3 different letters. And if we wanted to talk about the word Bob rather than the object Bob designates, you just put parentheses or quotation marks around it. Or not parentheses. What am I looking for?
Quotations.
Quotations or
Apostrophes.
Apostrophes, thank you. Kept thinking parentheses. So either put apostrophes or parentheses around it, and that means you're talking about the word itself and not the object it designates. So now this is a true statement. So Bob has 3 letters. It's now true. So the whole chapter, it's pretty intuitive. I don't think it's that informative going through the chapter. The only interesting cases you run into is when you get something like this. I say something like Bob is equal to California. So if I say Bob is equal to California, I'm saying that Bob and California are one and the same thing. This is somehow a different name for California, the state out there. If I say instead Bob equals the word California, and then I write Bob has 3 letters, this is false. But if I were to write after the fact Bob has, I think it's 10. Yeah, 10 letters, it's now true. Bob is the word California, and now Bob has 10 letters, it's true. So the only time it's a little bit interesting is when you're using designators to designate designators, when you're referencing words rather than objects. It can be a little bit interesting, but outside that, pretty much works as you expect, and it's not that informative going through the chapter.
So Bob's tree line looked like a symbol programming.
Yes, it's just a variable name. You can think about it as a pointer versus the value type. And so when we put this, we're talking about the pointer itself, and when we're doing this, we're talking about the thing it points to. That's the programming analogy. Okay, so that's all chapter 6 is about. Chapter 7 is just about informal proofs. Now, there is no formal theory of informal proofs. And so how do you produce an informal proof? Well, there isn't the right way to produce an informal proof. And the way to get comfortable with informal proofs is kind of to just drown in them. Expose yourself to a lot of them and get a feel for it. Now, I should warn you, if any of you were following along with me in the book, you probably noticed that the way that I prove something and the way the author proves something, I have my own style. And my style is not the same as the author's style. When it comes to informal proofs, there's even more style variance. And so you're going to see as I do informal proofs, I may have my own style. It's not the right style, it's not the wrong style, it's just a style. A common one that you may have come across before is like what do they call them? 2-column proofs from geometry. You might have done a 2-column proof way back in the day where you write your line of reasoning here and then that thing that justifies it here. So that's a style of proof. That's a style of informal proof. I won't be using that style. Style I use is just the one I'm used to. So nothing right or wrong about it. It's just the one I'm used to. And you probably have your own style if you did it yourself. So I'm only going to do one proof, full-fledged, here you go, not hiding any of the logic. Outside that, we'll start doing informal proofs. Now, the axiomatic systems that we're going to be using to get comfortable with informal proof, well, the first one we're going to use is group theory, and we already touched on this a bit last time. So let's remind ourselves of group theory, or maybe just quickly recap on axiomatic systems. Axiomatic systems in general, what are they? What are the 4 components of every axiomatic system? What does every axiomatic system have? Every axiomatic system is composed of 4 things. I'll give you a hint. 1, axioms. That's in an axiomatic system. What are the axioms? There are initial assumptions. There are starting statements that we're going to work with. Okay, what else do we have?
Undefined terms.
Undefined terms. 2. undefined terms. These are also called primitives.
Primitives?
Primitives, your primitive terms.
Why are they called primitives?
Because they're the primary terms that you're going to use to construct everything else. They're primitive. So we have axioms, we have undefined terms. Okay. Definitions. And once we have undefined terms, we can start combining those terms together to create definitions, defined terms. And then finally, the most important part of our axiomatic system,
Theorems?
theorems, the logical implications of our axioms, what it is our axioms entail. So that is our basic components of any axiomatic system. So we're over here in group theory. In group theory, we're not going to have any definitions. You don't need definitions, they're just nice to have. They're just ways of talking about a bunch of symbols all in one go. So we won't have any definitions, but we will have these three things. Now our undefined terms or our primitives, if they're undefined, how do we give them meaning? How do we know what they mean if they're undefined? What are our undefined terms over here? Let's look at group theory now.
The axioms gonna mean?
The axioms give our undefined terms meaning. So what are our undefined terms? What are our primitives looking over here in group theory? They're going to be all the terms that show up in our axioms that are not symbols of logic. So the logic that we are currently in is propositional first order predicate logic with identity. Okay, there's the name of the logic word. So here's group theory. Here's our axiomatic system. Let's really quick just recap it. Group theory, what is it? So it's some set G, this is going to be our domain that all our objects come from, together with this operation. This we call a group. These two things together, we call it a group if it satisfies these three rules. What are the three rules? The first rule is for all x, y, and z in our group, in our domain, x, I'm going to read this symbol as compose. That's just the name I'm going to put on, but this isn't function composition. This is any operation. And we did an example of what this could be. This could be the real numbers together with the plus operation. This could be the set just containing 0 together with the subtraction operation.
Oh, yeah, I remember now.
Okay. So, for all x and y, x compose y compose z is equal to x compose y compose z. So it doesn't matter what order we compose it. In the specific case, when the group we were looking at was the real numbers together with plus, this was saying x plus y plus z is equal to x plus y plus z. It doesn't matter how you add it. Axiom 2 is there exists something in G that we're going to call little e. There exists something in there, such that for any other thing you grab out of G, when I compose that thing with E, I get back that thing. So when I compose with E, I get back what I had. Or in other words, we say E is an identity element for this operation. Whatever that operation is, E is an identity element with that operation. When I do X, that operation E, I just get back X. Composing with E doesn't change anything. So this says there is an identity element in there. And then finally, this says for the example in arithmetic was 0 when we were doing plus and 0. So this first one was saying x plus y plus z is equal to x plus y plus z. There's one interpretation of that axiom. And then this one is saying basically there exists a 0 such that x plus 0 is equal to x. There's some 0 in R that makes that true for any x. This one now says for any x there exists an inverse element is the way I'm going to read that, such that x compose its inverse gives me back identity. So in arithmetic, the interpretation of that is for all x there exists our x inverse is going to be this x plus its inverse element gives us 0. The additive inverse is what we mean by a negative number. Negative 2 is the additive inverse of 2. So here is an interpretation of this axiomatic system. With me so far? Okay, question. What are the primitive symbols or the undefined terms in this axiomatic system?
It's a circle.
So, yeah, this operation, circle, I'll read it as compose. That is an undefined term in there. E, whatever the E is a constant in this system.
And it's undefined.
And it's not defined, but we know that there's an E in our domain, whatever it is.
Is it -1 by chance?
Yeah, that inverse symbol.
The inverse.
And so that inverse symbol is a primitive. And then what about equals?
I don't think so. Isn't that a thing of logic?
Right, that's a symbol of logic. Notice everything else up here is a symbol of logic. Parentheses, symbol of logic. For all, symbol of logic. X, Y, Z, variables, symbols of logic. Parentheses, and equals. Every other symbol that shows up in there is a symbol of logic. These are the only symbols that are not symbols of logic. And so they are our primitives or our undefined terms. Make sense? So those are our primitives. Trying to give you a sense for what the axioms are telling us. Now, let's jump into proofs. We're going to prove these 9 theorems, meaning these 9 things follow from these 3 axioms. Now, before we do that, one more thing I need to remind you of from last week. Another big focus of last week was, last week we finished up our theory for our logic pretty much. We finished up the rules that we need. We introduced identity. Or was that the week before? One of the two.
Last week was identity.
Either way, we introduced identity, right? And last week, another big focus was theorems of logic. These right here are theorems of this axiomatic system, meaning that these are logically entailed by these axioms. If these axioms are true, it turns out all these statements are also true. What is a theorem of logic? Because these are not theorems of logic. These are just theorems of group theory.
Do tautologies count or no?
Tautologies are rules of logic.
Or rules? Okay, yeah.
You could think about a tautology as a theorem of logic if you wanted, that's fine. So there's those.
What theorems of logic?
Yeah, what's a theorem of logic?
Something that you've proven if the
What you just said, didn't you?
Something you prove.
From an axiomatic system.
from
It's not dependent upon axiomatic systems. Our theorems of logic we can use in every axiomatic system.
That is the all the tautology.
So a theorem of logic is a statement whose premises are the empty set. It is dependent upon no premises for its validity.
Oh, okay.
That's what a theorem is.
So it's only a theorem if it has
It's a theorem of logic if these are its premises. This is not a theorem of logic because its premises are these, which is not the empty set. So if it doesn't depend on anything for its validity, you can simply derive it using the rules of logic, demonstrate it to be true, then it is a theorem of logic. And so all our tautologies do fall into that category. Yeah, you can call them all theorems of logic.
But there are some
But
outside that.
they were some trivial ones. There were other things we derived. So one of the ones we did last week is not there exists x such that some predicate about x gives us for all x not that predicate about x. How you distribute a negation over a quantifier. That was one of our theorems of logic. This is true independent of the system you're in. It is dependent upon no premises for its validity. This is a consequence simply of the rules of logic themselves, the rules of derivation. What are the rules of derivation I'm talking about? I'm talking about rule P, rule T, rule CP, etc. Those 7 rules that we have. That's what we mean by it's a theorem of logic. So before we start proving things in the system, I want to remind you of 2 extremely useful theorems from logic. And I call them here Theorem A, Theorem B, just so that we have some way of referencing them. So Theorem A, we showed last time that for all x, y, and z, if x is equal to y, then x star z is equal to y star z, where star is any operation. Assuming that this is defined in whatever system you're in. So you can't break the system you're in by making it give you a term that's outside of whatever the set is you're talking about. So if x is equal to y, then x, to give you an interpretation of this, if x is equal to y, then x plus z is equal to y plus z. Or if x is equal to y, then x times z is equal to y times z. Or if x is equal to y, then x divided by z is equal to y divided by z, as long as it's defined, which it wouldn't be if z were 0 in that case. Those would be interpretations of that. That's one of our theorems of logic. This is a consequence of the rule of identity. It doesn't matter what that operation is. So this is going to be true in our special system here, where we replace star with circle. Since it's true for any operation, it's going to be true for circle. What's circle? It's the operation that follows these rules. That's what circle is. And then the other one just told us that we can do it on the other side. And we have to be a bit careful keeping track of what sides we can do things on. So our other one was for all x, y, and z, if x is equal to y, then z star x is equal to z star y. So I can apply the same operation in a term on either side of equal terms I want. And this is what gives you, in your basic algebra, you can add the same thing to both sides, or you can subtract the same thing for both sides, all that. That just follows from these two rules. Make sense?
So you can use the theorems of logic along with the theorems.
Yes, so these theorems of logic can be used in every axiomatic system. They can be used in group theory. They can be used in geometry. They can be used in algebra. They can be used in any system you're in. Because they're just consequences of logic. They're more foundational than any of those systems. That make sense?
Yeah.
Good. So let's start now with Theorem 1. We'll do our proof of Theorem 1, and then this will be the only full-fledged proof we do because it gets kind of tedious. So our first proof, we are going to prove that for all x, y, and z, comma, if x circle z is equal to y circle z, that implies x is equal to y. Okay, here's what we're proving. So, 1, how are we going to start this proof? You know. What are we trying to prove?
Okay, first we've got to we can assume. Okay, we're not going to do.
Assume the antecedent.
Yes.
Yeah.
I just want to clarify we're not going to do universal generalization or whatever.
Well, we will need to do that here in a second, but here's just, we're going to introduce this as a premise. X circle z equal to y circle z. We are introducing this using rule P. We can introduce a premise at any point. And it is dependent upon premise 1 for its validity with 5 variables x, y, and z. Right? Okay. 2. Now, here's the things over here that we can use. It's often very helpful to think about what our proof idea is going to be and kind of scribble that to the side. So let's kind of just scribble down here and we'll erase it when we're ready to move forward. So I know x circle z is equal to y circle z. I'm trying to somehow get that x is equal to y. And if you're stuck with that, let's imagine it in a very concrete case. If I knew that x plus z was equal to y plus z, how would I show that x is equal to y? Well, just imagine you were in some algebra class. What exactly would you do to now show that x is equal to y?
You would just subtract a z.
You would subtract z from both sides, or to say it in terms of addition, you would plus minus z to both sides. Right?
Yes.
And then adding minus z to both sides, then you get x plus, what's z plus minus z? 0 is equal to y plus 0. And what's anything plus 0? It's just that thing, and it's just that thing. So we're going to do a similar approach here. I'm going to take x, I'm going to take this side, and I'm going to apply the operation of its inverse element to that side. And what I do to one side, I can do to the other. So I'm going to do y circle z inverse. It's the exact same thinking. Add its additive inverse. Circle its inverse. Whatever it is. With me?
Okay, I was wondering how that worked.
Now, how can I go from this to this? That's using rule A here. If two things are equal, you can do operation some new symbol to both sides. Operation some new symbol to both sides. And now we're going to use associativity. Notice that that's what this one tells us. That you can move the parentheses. So parentheses here, you can move them over here. So move the parentheses now. That gives me x circle z inverse is equal to y circle z inverse, with the parentheses there, with me? And now what is z circle z inverse?
Z.
What was,
Oh, 0.
almost,
Oh,
x plus it, or z plus its inverse gave us its identity element. What is z circle z inverse going to give me?
oh, E.
It's going to give me its identity element, whatever that is, which is e. So this is the same thing as x circle e is equal to y circle e. And now what is x circle e?
X.
It's just x. X circle its identity is the same thing as x plus its identity. It's just x. So x equals y. And so here's our scratch thinking. You with me?
Yes.
So early on, these can be kind of tough because you're in some weird system, hard for you to think about. Sometimes it's easier to go to our interpretation, like arithmetic, figure out how we solve it in arithmetic, then translate it to our symbols here, and then actually write out the full proof. So we got this. What was the first thing we did?
We circled the additive. Or
We circle z inverse, right?
Yes.
Now, notice that first we got to get that z inverse. This is kind of our scratch work, so we weren't being too careful in our reasoning. How do we know that there is a z inverse?
Axiom 3.
Yeah, so we're actually going to have to use both universal and existential specification. I'm not going to do it in 2 steps. So we'll do it all in 1 step. But I know that there must exist something out there called z inverse. I know that there exists z inverse such that z circle z inverse is equal to e. This was using universal, both specification and generalization. So I'll just call it universal on axiom 1 or axiom 3. You with me? Okay. So we got that. Now what did we want to do? So I now know that z inverse is in our domain.
Right.
So now we can
Okay.
continue to this step.
Alright, I just want to get on the same page. We're just trying to redo what we just did.
Yeah, this was our scratch thinking where we weren't being careful to list out every step.
So we're starting over, but more explicitly.
Right. So here's what I scribbled out right here is pretty much what we're going to mean by an informal proof. An informal proof is the scratch work you would need to write out a completely formal proof.
Is it like writing or having your model in geometry where you just like sketch out what it would look like first?
Every proof you do in geometry is an informal proof. All the proofs we do in mathematics are informal proofs. And so in geometry, I don't make you list out every rule of logic that you're using. That would be insane. Your proofs would be humongous. You're just kind of trying to give me an idea for what your thinking is doing and when you're using what postulate.
Yeah.
And so it's very fast and loose relative to logic. And so this is very fast and loose relative to logic, the thinking.
Yeah.
So this is what we'll roughly mean by an informal proof. We'll get more of that down the road. It's going to be our scratch work that we need, but now let's just keep following our scratch work. Okay, so now we've got z inverse, so we're ready for this step. Right? So now I can just say 3, then x circle z inverse is equal to y circle z inverse. Now how did we justify that? How did I know that I could circle z inverse on both sides? How do I know that's a valid thing to do? The thing that says what you do to one side you can do to the other. Where do we get that?
That's a theorem of logic.
It's a theorem of logic. That's theorem A here.
That's
Theorem A says that if you have 2 things that are equal, apply some operation and some term in your domain to both sides and you're good. That always works. Here we just need to validate that z inverse was in our domain.
right. So
It
now-
was an object.
Okay.
So now we circle it to either side. This was using a theorem of logic, which we called theorem A.
telling me the entire point of the second one was just to show that the inverse of z exists.
Yes.
Interesting.
Just to simply state that there is some, because that's what this says. It says for all z, there exists a z inverse such that z circle z inverse is equal to e. So my z was given to me on this line. This, this is also dependent upon 1 because we're using the same z. Sorry, that probably added confusion. So this is 1 xy, xyz, together with axiom 3. Because we were universally specifying with that z right there, that particular z. So this z is related to that z. We're picking that same z. Okay, so that's where we're specifying. And then this one, that's just using a theorem of logic, and so we are dependent upon the same premises that the previous one was on. Because the theorem of logic adds no new premises. It's something we can always and forever use. Okay, so that gets us to here. Now what?
You can move the parentheses.
How do I know I can move the parentheses?
Because of the axiom 1.
Axiom 1, so we're going to universally specify on axiom 1. So then I know that x circle z inverse is equal to y circle z inverse. This is using universal specification on axiom, what was it? 1. And now we are dependent upon axiom 1, axiom 3, and premise 1, and we'll just remember premise 1 has flag variables. Okay, so now we're there. Now what?
We can, we know that z and z inverse is e. So axiom 3.
Well, we don't need to use axiom 3 now. We can use line 2 from our proof. We actually already universally specifies that. And so this is actually going to use identity. Remember, identity, loosely speaking, we have 2 rules for identity. The first rule of identity is that everything's identical with itself. And our second part of identity is
Equals added to equals or equals. Or no?
equals substituted for equals.
Oh, it's a substitute.
Equals may be substituted for equals. Equals added to equals or equals is what this is saying and what this is saying.
Right, but it's a substitute.
So this was a consequence of our rule of identity, but our actual rule of identity, rule I, that was one of our, I guess when it was all said and done, we had 8 rules. Let's just really quick make sure when I say my rules, we understand exactly what I'm saying. I mean as in P, CP, T, US, UG, ES, EG, and then finally I. And as in I, that rule, that's what I meant. The rule of identity has 2 pieces to it, which is everything is identical with itself and equals may be substituted for equals. So this is equal to that, so equals may be substituted for equals. So substituting in down here, I can now say x circle E is equal to y circle E. And this is using identity, and we're substituting from line 2, and we still depend upon the same premises.
On line 2, the U is what rule exactly?
This was universal specification and universal generalization, and existential specification. Oh, I should have done S because we were specifying both those. Because we were getting rid of this quantifier and then getting rid of that quantifier all in one go.
Okay.
Yeah, should have just written it out. Okay, that's a dot, not comma. Okay, I think we're all on the same page.
Yeah.
Okay, so that's 5. So now 6. What's next?
Now you can use that theorem of logic, I believe. Wait, you can't use that.
Yeah, I got x circle E is equal to y circle E. In terms of arithmetic, what's this saying?
X plus E.
X plus, what is our identity with plus?
Oh, negative. Or
Negative x.
What is our identity with plus? What is a number such that when you add to, you get yourself back?
it's the negative of the number.
Now,
Subtract the.
that's the inverse. What is a number I can add to x such that the result is 0? There you go. Yeah. So this is saying x plus 0 is equal to y plus 0. In arithmetic, how do we handle that?
You just cancel out the zeros.
You just get rid. What? How do we know we can do that? It's because we have an axiom a lot like this one, the one that tells us our rules for how our identity element functions.
Why am I seeing that?
So axiom 2 says x circle e is just x.
Yeah.
Or in our interpretation, x plus 0 is x. It's saying e is our identity element for this operation, this operator. And so, I can write, this is where it's kind of annoying right now to all the steps. X circle e is equal to x, I'm going to do it twice, and y circle e is equal to y. This was doing both our specifications, universal specification on this. So I'm doing both, I'm using this twice, for that and for that, where I'm plugging in this variable for one and this for the other. So this is universal specification twice on axiom 2. And now we are dependent upon, I don't know why I wrote the 2 there. We are now dependent upon axiom 1, axiom 2, and axiom 3 for our validity together with our premise 1. With me? And now I can use rule I. I know x circle e is equal to x, and we have an x circle e there. Similarly, I know y circle e is equal to y. We can substitute in there. And so now, erasing our scratch work, I think we're good. 7, we can say, therefore, x is equal to y. This was using identity on lines 5 and 6. That's how we were substituting. We were substituting 6 into 5, but you can piece that together. And now, we are dependent upon our validity. The exact same thing. We're still dependent upon everything, right? Axiom 1, axiom 2, axiom 3, and premise 1. Okay. And now what do? We got where we were trying to get. But
Then we can prove that it implies it by
Generalize.
for all. Yes.
so we can't generalize yet because we still are dependent upon premise 1, which has 5 variables.
Oh, conditional premise.
Yeah.
Rule CP, right. So now we can say, therefore,
X circle z equals y circle z implies x equals y.
and this was using rule CP from lines 1 to 7. And now we are just dependent upon for our validity. I'm just going to use fancy P for all the axioms.
Yeah.
And now 9, now we can universally generalize. And now we can finally say, for all x, y, and z, x circle y equal x, x circle z equal to y circle z implies x is equal to y. And that was using universal generalization, and we're still just dependent upon all our axioms for our validity, and we're done. Okay, so that's the only one that we're going to bother. Even then, we were kind of skipping some steps because it just takes too long to write everything out. It's real tedious. So now we're going to start transitioning to informal proofs, which you see how our scratch work, it kind of got at the heart of the proof. So that's our goal with informal proofs, is to do enough of the scratch work that you felt like you could take that and actually write out the full proof now with all the actual steps in there. And we're going to skip some of the tedious steps. For example, once we do this, implied this, we didn't need to bother with these 2 steps. That's super boring. We know that's the same steps every time, stuff like that. So let's now prove Theorem 2. Theorem 2 is this one. For all x, x circle e is the same thing as e circle x. So it doesn't matter what side your identity element is on when you circle with it, it still just gives you back x. Because we already know x circle e gives you back x, so e circle x must also just give you back x. Make sense what we're proving?
Are we going to do the same thing, or are you say we're just doing scratch proof?
So now we're just going to do a scratch proof.
Gotcha.
We're going to do an informal proof. That's what they call it, an informal proof. So how am I going to write this one out? I'm going to start out with x circle e and somehow get it to equal e circle x. Or let's see, which one do we know how to work with? We know how to work with x circle e, so I'm actually going to start with e circle x and keep messing with that until I can get x circle e to come out of it. So 1, and we might say something like, observe. My own style, I choose to number the lines on my proof. You've already seen that from how I do it here. And the idea is every line, every number corresponds to a complete sentence. Still trying to function in terms of propositions here. Write down propositions. So observe that, well, we won't write the that because we'll run out of space here. Observe x circle e is equal to, what do I know x circle e is equal to?
X.
Oh, sorry, I want to start with e circle x. Start with the one that we don't really know what to do with and try to get to the one that's more workable. So the one that I don't know what to do with is the e circle x, right? E circle x let's see, what can we get that equal to?
Can I get it to x circle? Well, I don't know if this is helpful, but you get it to
E circle x, just replacing my e here. My e is the same thing as x circle x inverse.
Yeah, that's what I was thinking.
So rewrite that. That's the same thing as x circle x inverse circle x. Now,
You could do
let me think what it is I want to do. I want to get
axiom A. Well, that's helpful.
so far this was just using axiom 2, right?
Axiom 3.
Axiom 3, thank you. So this was using axiom 3. Now I'm going to rewrite this as e circle x circle, let me move to the left here, keep our equals in the same spot. E circle x inverse then is equal to x circle x inverse circle, keep my parentheses correct, then we were circling with x, and then we were circling x inverse, doing the same thing on both sides, right? Okay. Oh, no, that's fine. Okay, I think I see it from here. Sorry, just had to play with it to make it quick in my mind. So I'm trying to get, my idea here is I'm trying to get e circle x to ultimately I'm going to get to equal x. And so my thinking is I'm going to try and get it to equal this x. So if I can get this e circle x to equal this x, this, what did my previous rule tell me? It says I can cancel out the same thing on both sides. Notice how this is different. What we just proved is different from what this rule says. This rule says add the same thing to both sides. This is a rule that says you can also cancel it out. And notice that canceling out is not a theorem of logic. That actually was dependent upon these axioms to say we can actually cancel it out. So I know I can cancel out the same thing on both sides. So if I can get this piece to equal this, and I can cancel out that with that, I just need this stuff to go away. So my goal from here on out is to get this other stuff to go away. So I'm going to use associativity to move my parentheses around. So this is equal to x circle x inverse circle x inverse. You with me? So going from here to here, what did we use? We used Theorem A. That was just using logic, saying I could do the same thing to both sides. Going from here to here is using associativity,
Which is A1.
which is axiom 1. And now, what is this? X circle x inverse. It's just E. It's our identity. So this is the same thing as x circle x inverse all circle E.
Don't you want to do the other way around?
No, because I know how to do it when the E shows up on the right side. I don't know what to do with the E on the left. That's what this whole thing is working with. Our theorem is, right now if an E shows up on the left, we don't know what to do with it. We know what to do when an E shows up on the right, we can just get rid of it. So I need to mess with this, somehow make an E show up on the right,
Okay.
and now we can get rid of the E. So what is something circle E?
That's something.
It's just a something. Circling with E just gives you back identity. Anything circle E just gives me back that thing.
And that just gets right back where we started.
So this, going from here to here, we were using axiom, what do we use? That one was 3, right? And now, this is equal to x circle x inverse. Circling with E just gives you back whatever it was. And so now that's using axiom 2. Right? And so now what do I have? Just to rewrite it. So, let me rewrite 2. So then, I have that E circle x inverse is equal to x circle x inverse. That's what I have so far, right? This is equal to that. This is equal to that. With me? Now, what did my previous theorem say I could do? If I have two things circling the same thing, those two things are equal. I have two things circle same thing.
So E circle x equals x.
So E circle x is equal to x. That was using theorem 1. Right? But it's also equal to x circle E. How do I know that?
Axiom 3.
Axiom 3.
Or, no, not 3, it's 2, sorry.
Axiom 2. So 3. Therefore, E circle x is equal to x circle E. And so now it doesn't matter what side the E shows up on, we can always flop it around.
Would you be able to give us some intuition for the purpose of group theory and how it applies to real world situations?
No. Mostly because you don't have good exposure to other systems of math. Typically, the last 2 times I taught logic, I was teaching a bunch of kids who had already taken something called discrete math. And that introduces you to just a bunch of different systems of mathematics. And so, since you don't have good exposure to systems of mathematics, it's hard for me to use them as examples. Like, you kind of just have arithmetic. Like, the most common one would be using that as actual function composition and talking about permutations. That's like one of the most common ones to use as an example. But permutation is a particular type of function, and I'd have to give you the set theoretical definition of a function, which is a type of relation. I'd have to give you the set theoretical definition of that, and it's just a whole can of worms.
You couldn't even explain it in like a...
Well, I tried to last time in kind of a basic way, is that operations that function this way show up in a bunch of different fields of mathematics,
Does it also show up in geometry?
which would be a field of mathematics.
Yeah, I mean, couldn't you give us a visual explanation of how that's...
So it's logically equivalent to a permutation, but it's like different orientations of an object somehow is connected to this. It's so hard to give you intuition because the most basic one is permutations, and you don't have that. But yeah, so they use group theory to do analysis of like Rubik's cubes, for example. And there's a way of expressing that, all the different permutations of a Rubik's cube. Anything you have permutations of, we use group theory for it, but you don't know those. So
It shows up a
And
lot
you
in
learn
discrete
those
math.
from discrete math.
yes, so in discrete math, part of discrete math is just covering a bunch of different because another one is modular arithmetic. I could do this with modular arithmetic, but you don't know what modular arithmetic is. You have good intuition for it because you program and you actually use it. You just don't know what it is and you don't know symbols.
Yeah.
And so I can't use it as an example. So I'm stuck without very many examples. That's my problem.
It's just hard to...
But it's kind of a good thing that you don't have any examples. And you just have to think about what exactly it gives you,
Okay.
instead of having that pretty intuition to fall back on. Now, we gave you the plus because it can help you figure out how to do a proof when you get stuck. But, yeah, sorry. square box. Of course. Okay, so let's move on to Theorem 3 now. So Theorem 3. What are we proving? We're proving that for all x circle x inverse is equal to x inverse circle x. Now I know that x circle x inverse is identity. That does not mean that I know x inverse circle x is necessarily identity. And that's essentially what we're going to be trying to prove here. So, I kind of want a way to make both those show up. Let me start with this. So I'll say, observe that we have, where am I going to want my parentheses on the first one? Which one do we not know how to work with? So we know how to work with this one. We don't know how to work with this one. So I'm going to write my parentheses to capture that. Sorry, a lot of thinking in my head. Let me just write it. X circle inverse, x inverse circle x inverse is equal to x inverse circle x inverse. So that is just using axiom 3, literally writing this out, substituting in x inverse x inverse. So this was just coming, not axiom 3, axiom 1. So that's just using axiom 1. And the only reason I kind of thought to do that is because I wanted to get this thing to show up on one side and this thing to show up on another side. And I always like the thing that I don't know how to work with to be on my left, just preference. So the things I don't know how to work with over here, the things I know how to work with to manipulate over here, and then I do my manipulations on the right hand side. And that's another one that's just my own personal taste. So this is equal to, we'll just keep carrying over the equals. So this is equal to, let's see, how do I know how to work with this thing? What's something I know how to do with this? Rather than just moving the parentheses, that gets me back to here. So what's something else I can do?
X circle x inverse is e.
Right, so x circle x inverse is e, so I can replace this with an e. Now that's promising because my last theorem says I can do something with an e. And it's not that uncommon that you need to use your previous theorem to prove your next theorem. They usually have a logical order. We had to use this to prove this. It's not far-fetched that I need to use this to prove that. So let's do that. That's x inverse circle e.
So nice that people do this all in order.
Yeah, we don't have to think carefully about the order to put these things in. They basically line out the path for us and say, now start walking. It's like they drew the map. This was x inverse circle e. Okay, now you might be tempted to say, now let's get rid of that e and say it's just equal to x inverse. But I don't want to do that because I know how to do something cool with e's now. What can I do with my e's? Okay, yeah, now I see it. What do I know how to do with my e's?
Circle with x if they're equal to. Well,
Notice that none of our rules here let us move symbols around really. They just let us move the parentheses. We don't have that nice commutative property. The commutative property is the one that says a plus b is equal to b plus a. We don't really have that, so it's hard for us to swap symbols around here. We have to come up with clever ways to do it. Fortunately, what does this let us do?
swap.
Swap the e. And so now I know that this is the same thing as e circle x inverse. Now keep in mind, I'm basically trying to show that this is equal to e. I'm trying to say x inverse composed with x is equal to x composed x inverse, but x composed x inverse is e. So I'm trying to show that this is equal to e.
Oh, okay. I see.
So then what? So I know that this is equal to this. I want to say that this is equal to this. That pesky thing on the right-hand side is bugging me. on the right-hand side of both of them is bugging me. If only we had a cancellation rule for things on the right-hand side. Fool me, you fool me. We had something that said when you have two things that are circled with the same thing, those two things were equal. Okay, so I got this, circle that, is equal to this, circle that. Notice that they're circling the same thing. And so I get this is equal to this.
Oh, okay, that makes
You see it?
sense.
Okay, so then x inverse circle x is equal to e, but I also know that e is equal to what?
X circle x inverse.
X circle x inverse. And so there we have it. X inverse circle x is equal to x circle x inverse. I don't know why I put parentheses here. That was completely pointless. You see it?
You're saying you used
Oh,
theorem
so
one.
then you used transitive. Okay. Yeah. I see.
So in going from this line to this line, what did I use? I used theorem 1.
Just theorem one?
Theorem 1, and then
Axiom.
going from here to here is using axiom, what is it?
Axiom 3.
Axiom 3.
Yeah.
And on this line, we started out using axiom 1. That's how we get this is equal to this. Going from here to here, that's again using axiom 3. And then going from here to here, that was using theorem 2.
Oh, well, okay.
And so then I got this was equal to this. Using theorem 1, we can cancel out the x inverses on both sides. So I get that is equal to that. But E is the same thing as x compose x inverse. And so this theorem gives me that x compose x inverse is the same thing as x inverse compose x, it's just identity. Or in terms of our arithmetic, it tells me 3 plus negative 3 is equal to negative 3 plus 3 is equal to 0.
Or 0 in the middle, but yeah.
Where's 0 in the middle, I guess, for how I have it written up there. Yeah. And the negative 3 in the wrong spot. But same idea. See it?
Yeah.
Okay. So next theorem, what are we proving next? Theorem 4. We're proving that if x compose y is equal to x, then y was secretly our identity element. Or in other words, there's only one identity element. If you can find some other y, such that when you circle with it, you get back what you started with, then that y must have been identity. It's the only thing that behaves that way. Okay, so theorem 4, we want to prove for all x and y, if it is the case that x circle y gets you back x, then it must have been the case that y was secretly your identity element. No way around it.
Right.
Okay, so this one, a bit easier to figure out how to prove, because it's a implication. We love those. We don't even think about how to start these. We just instantly start with let or assume, whatever word you want. Let or assume x circle y equal x. Okay, always start that way. 2. Then what? Let's think about the arithmetic version of this for a second. Imagine that I told you that x plus y equals x. We're trying to prove y then must be 0. How might we prove that? And remember, instead of subtracting, say add a negative. And then we're following a similar thing.
We already know the y0 in that case.
How do you know y 0 here? So imagine you start with this algebra problem. This shows up on your test. It says, given that x plus y equals x, prove y equals 0. So we're in an algebra class. What do we do with this?
I've always said I would just assume that it's 0 because logically. But so my intuition would jump across this whole thing.
Okay.
How can I show y is in fact 0?
Can you add 0
Sure.
To say.
All right. Maybe just to remind us where we started. Okay, so this is equal to x plus 0. Okay, adding to 0 doesn't change it.
And then you subtract x to both, or add
Negative x to both sides.
And then you have y
So
equals
we'll
zero.
say that negative x plus y must then be equal to, forget that 0 now, it's not doing anything for us, negative x plus x, right? I added a negative x to both sides.
Yes.
So we started there, add the negative x to both sides. Associate this with this, and this with this, right? What's negative x plus x? 0. Plus y is equal to 0. What's y plus 0? Y. So y is equal to 0.
Oh, got it.
So we're going to be doing the exact same thinking. All right, so we start with x circle y equals x. So then what did we do next?
You added oh man, I already lost the word.
The inverse element.
The inverse element.
We circled the inverse element to both sides.
Yeah, that's correct.
So we're going to circle x inverse over here. So now x inverse circle with, now we were already doing these ones first, so we have to keep these parentheses the same. I don't know why I'm writing so slanted. So then, x inverse circle x circle y is equal to x inverse circle x. Right? Okay, so now what?
You can move the axiom A, or yeah.
Axiom what?
Well, can't you move the parentheses
Yeah, what tells us we can move the parentheses?
in that axiom A?
Axiom 1.
Oh my heck. Yeah.
But yeah, okay. So that gives us that. We can say that x inverse circle x circle y is equal to x inverse circle x. So we got to there. Then what?
Using theorem 3 and theorem or axiom 3. So theorem 3 and axiom 3, we can determine that it's E.
Perfect. So then we know that x inverse circle x
Is equal to
x circle x inverse, which is the same thing as E. So we'll do that all big jump in one go. So then E circle y is equal to, what is this?
Another E.
Just E. Right?
and that's on the implied on the other side of the implication, right?
Well, there's just a period there. So then new line. So this follows from this, right? We just replace that with an E and that with an E, which we know we can do from our previous theorem. And axiom 3 or whatever.
Right.
Right? So then that is equal to that. So then what can I conclude? That y is equal to E. Y is equal to our identity element.
How did we
Because
make that jump?
identity circle y is the same thing as y circle identity, which is y.
Oh, that's right.
So we were using this theorem to swap the order, and then this to get rid of the E. So swap the E, then get rid of it.
Okay. Yep.
Cool. So let's try another one. So our next theorem here is, that was 4, right? So we're on 5. Okay, so now we're going to do a left-hand cancellation law. Up here, we said when you circle with the same thing, you can cross it out on the right-hand side. Now we need to show that when you circle with the same thing on the left-hand side, you can cross it out. Two different things. And notice how much more infrastructure we needed to prove this compared to this was the first thing we could prove. So, Theorem 5, we need to prove that for all x, y, and z Was this right-hand cancellation or left? Can't remember. Left-hand cancellation. Z circle x equals z circle y implies x equals y. That's what we need to prove. All right, line 1, what are we going to do? Assume the antecedent. So we say let x, y, and z be in our domain such that z circle x is equal to z circle y. Okay, now what? I've been super lazy in Theorem 2, 3, and 4. I'm going to give a more full informal proof this time. So let me do a more full informal proof because I'm being pretty lazy. So here's how we should actually write this out. Let x, y, z in G. So let x, y, and z be any elements from G, whatever our set is that all these things come out of, such that z circle x is equal to z circle y. So we grab 3 random things out of there, such that this is the case. I need to show for any 3 random things you grab out of there, you also made this the case. You made this the case, you also made that the case. So the next one is 2. Then I know that there must exist z prime, or z inverse, not z prime, z inverse in G, such that z circle z inverse is equal to E. And how do I know this? Axiom 2. So maybe even write by axiom 2. Axiom 3. So axiom 3 tells me for anything you pick out of there must exist an inverse element that makes this true. Okay, so then 3. Now what am I going to do? I'm going to put that z inverse in front of both of these to cancel out with the z. I'm going to be left with the x equals y. But we're going to do that over more steps.
This whole problem just seems almost identical to Theorem 1, except for the reverse.
Well, we'll see how it changes it. So then z inverse circle, whatever we already had there, z circle x, is equal to z inverse circle z circle y, and this is by our theorem of logic right here. So I'm going to call it Theorem B. So then 4, then z inverse circle z, circle x, is equal to z inverse circle z, circle y, by what one is that? A3. Tells me I can move the parentheses around. Right?
Yeah.
From there to there, just move the parentheses around. Now what does z circle, or z inverse circle z equal?
The E, right?
Yeah, we're going to be a bit more full this time, since I was being super lazy before. Z circle z inverse. Z inverse circle z is the same thing as z circle z inverse, and I know that from Theorem 3. So see how I had to use this fact to prove it?
It's true.
So z circle z inverse circle x is equal to z circle z inverse circle y by Theorem 3, 6. Then E circle x is equal to E circle y, right? That's using axiom 3. And then this gives me that x circle E is equal to y circle E. And that's using moving the e's to the opposite sides.
Yes.
Theorem 2.
Okay.
So 7, then finally using whatever the axiom is, maybe just write therefore. Therefore, x is equal to y using finally axiom 2, I think. Yeah,
I guess, yeah.
because we just replace that with an x and replace that with a y. Okay, so there would be a more full version of an informal proof. And notice that this one had a lot more thinking going behind it than our first one did. Because we had to use this fact and we had to use this fact in order to justify it.
Right.
And so even writing out informally, if we were full, that still came out 7 lines, while that one came out 9. So if we had to do the full proof for this like that, it probably would have taken us like 12 lines or whatever. Okay, but I won't even bother writing my informal proofs that full anymore. And we'll stick mostly with just scratch work because I think it's typically enough for you to get the idea.
No, yeah, I prefer it actually.
So theorem 6 now, if x circle y equals E, then y is equal to x inverse. So we need to show that for all x, y, and z, if x circle y is equal to E, that implies y was secretly x's inverse. Let me give you a concrete example of this. If I knew that 3 plus y was equal to 0, that must have meant that y was equal to 3's inverse element, namely negative 3. That's concretely what that's saying, or an interpretation of what that's saying. Okay, so how are we going to prove this one? Line 1.
X circle y equals E.
Perfect. Let x circle y equal E. Start by assuming our antecedent. Now I'm trying to show that y is equal to x inverse. So I want to add an x inverse to both sides. So this gives me that x inverse circle x circle E, or circle y, is equal to x inverse circle E. Okay, now what can we do? We're trying to ultimately get the y equals the x inverse.
Move the parentheses.
Move the parentheses. So this gives me that x inverse circle x, circle y, is equal to x inverse circle E. Okay?
We make the x inverse circle x and E.
Yep, that's the same thing as x circle x inverse, which is the same thing as E. So we can say that E circle y is equal to x inverse circle E, I guess. Well, let's just circle it with E. What do I get when I circle that with E? I just get x inverse. X inverse circle E is just x inverse.
That's correct, yeah.
X inverse circle identity element gives me back identity. Same thing we passed in. Okay, and now what?
Lost track of where we're trying to go.
We're trying to get that y is equal to x inverse.
So using theorem 2 and then theorem axiom 2.
Yeah, theorem 2 to swap those, so that's the same thing as y circle E. And then when you circle with E, what do you get?
Just get itself.
Itself.
Itself. So we just get y is equal to x inverse. And we're done.
This is coincidence. Axiom 3.
And that's by axiom 3, or axiom 2.
We used Theorem 2 to swap it,
Right.
and then Axiom 2 to get rid of the E.
Right.
What if they intentionally
Or
make
axiom, yeah.
Axiom 3 and Theorem 3 the swap of it, and then Axiom 2 and Theorem 2 the swap of E, where the other one is a swap of the inverse. And
That
they
could very well be the case.
They intentionally did that probably.
Probably. No idea. And I'm not even positive. I wrote them down in the exact same order that the author did. But I do know that I took the time to prove them when I wrote them down, so I know that they're provable in this order. Not as much as I know. I wrote these notes down way too long ago to remember. Okay, any questions before I move the camera? So now, those last two columns, I don't know if it matters, I don't have that whole thing. All right, so our next one we are proving is Theorem 7. And Theorem 7 says, the inverse of the inverse gets you back the element. So for all x inverse inverse is just x. Or in terms of our arithmetic interpretation, this is telling you that negative negative x is just x. Negative negative 3 is just 3. Okay, so how are we going to prove this one? Observe, let's start with our x inverse inverse, and we want to somehow show that that's equal to x. So we'll start with that, it's equal to
Would it be E inverse or no? No, it's not.
So what can I do to it and not change it?
You can add
Can circle x. Yeah, circle x both sides. Or no?
Yeah, circle x both sides.
But I don't really know what this is equal to. I'm trying to show it's equal to something. So I need to manipulate this such that I don't change its equality. So
Just trying to.
what can you add to a number and be guaranteed that you never change the number?
0.
0. What can I circle to this and be guaranteed I don't change it?
E.
E. So let's start with that. That's like the only way we can really start messing with this.
X circle E. Or.
Just circle E to it. And we didn't change it.
Oh.
I took it and I just circled E on there. I added 0.
So it's the same thing.
So it's the same thing so far.
Yes, okay.
Now what can I replace E with?
X circle the inverse x.
X circle X inverse. So I'm going to write this as X inverse inverse circle. I'm going to write it in a more telling way. X inverse circle X. X inverse circle X is still just E, right?
Correct.
So I took that E and I replaced it with X inverse circle X. Okay, now what?
Change. Or can we move around the parentheses? Was that not?
Yeah, we can move those parentheses
Yeah.
like that. So we can rewrite this as associate these two terms together.
That's with.
And so we can call it X inverse inverse circle X inverse circle X. Okay. Now what? I have something circle its inverse.
Well, you have an inverse circle is inverse.
I have some symbol inversed circle that same symbol again.
Oh yeah. Yeah, okay.
So a thing circled together with its inverse is
E.
E. So this is just E circle X, which is equal to
X.
X.
Nice.
We did it. Woohoo. All right. Theorem 8 says, what does Theorem 8 say? For all x and y, there exists a z such that x is equal to y circle z. For all x and y, there exists some z out there such that x is equal to y circle z. So, for any two elements, I can always circle something onto it to get the previous element. It's like pick any two numbers you want, 1 and 17. I can always add something to 17 to get 1. That's what it's saying. Pick any two numbers, there's always a third one out there you could have added on to make the second equal to the first. For any two elements of our set, there's always something we could have circled on to make the second one equal to the first. So I kind of want this z to somehow undo the y and be left with an x. Don't really know how to give you a hint for this one without just writing the first line. What? We're trying to come up with a z here. So maybe write my first line here. Let x and y be any two elements in G. Okay, so we got any two things, x and y out of G. We grabbed them. Now I need to find some z such that when I circle it, such that when I do y circle z, I get x back. What z here would make so that we ended up with x? If I did y circle what? What could I write here such that when I evaluate it, I'm left with x?
So that you're left with x.
X minus x circle y or something like that. X circle z.
Isn't it e?
Oh, I think I might. Shoot, what is it?
We need to find something that we can put there so that when we evaluate this, it comes out x. So first thing we need to do is somehow get rid of the y. How can I get rid of the y? What's a symbol I can put here that when I circle with it, it kind of gets rid of my y?
The inverse of y.
Y inverse. Okay, so that will get rid of my y. Now what do I need to get to x?
X.
X. Okay. So let x, y, and g, comma, and let z equal y inverse circle x. Since x and y are two things in there, y inverse must also be in G, because y is in G, and every element has an inverse. And x was already in G. And circle, anytime it takes two elements out of G, it spits out another element in G. So z is now an element in G.
That makes sense.
So 2. Then y circle z is equal to y circle z is equal to, move our parentheses, y circle y inverse circle x. And I think you can see those cancel out to 0, or to identity. Identity circle x just gives me x. So we found the z such that y circle z gave us x. Now let me show you in a concrete case what we just did. So in the concrete case, let's say that our x was 2 and our y was 7. We were looking for what z could we add there. We said, let's add the inverse of 7 and then the x. Here's the number such that when you add it with 7, you get 2. What's the number? Negative 7 plus 2. The thing we need to cancel out 7 and have 2 remaining. Right, it turns out it's 5, but just showing you it as the exact same.
Yeah.
Yep.
I was kind of going that direction, but I couldn't quite formulate it.
All right, let's try the next one. Next one's very similar.
I love that these are all like 1 or 2 lined groups.
Yeah, group theory, it's a great, it's one of the reasons you cover it in discrete math. You're looking for simple systems to just expose kids to a bunch of different mathematical systems and help expand your intuition. Stop thinking math is, that's when you, what are we doing? Are we counting or are we doing geometry? And that's math, right? You're either adding and multiplying numbers or you're doing geometry. Okay, so the next one is going to be, for all x and y, there exists a z such that x is equal to z circle y. So notice it's different, but similar. So 1, start with the same thing. Let x, y, and g, comma, and let z equal. Now we got to figure out what we want our z to equal. This time, what do we want our z to equal? So I'm looking for x is equal to something. Circle y. What can I put here?
Same principle, isn't it?
Very similar idea. Very similar thinking.
It's like the inverse of y, and then circle x or something.
Okay, let's see if we can mess with this. So you're thinking this could be, well, ultimately equals x. Let's mess with it. Can I get this to equal x somehow?
You can we move them around so that
We don't have commutativity. I can't swap these things positions. That's the hardest thing about group theory is you want to just swap things.
Oh, that's my problem. That's why
yeah,
it won't
you
work.
want to.
So let's go back. We're looking for the z that we can plug in there. So that circle with y gives us back x.
So maybe the inverse of
The
x.
The other order, if that's what you mean by inverse, yeah, just x circle y inverse. Not y inverse circle x,
That's what I meant to say.
x circle y inverse.
So that you can move
And
them.
now those two can cancel out. So you can only cancel out the things next to it. I can't have a y inverse, a y here, circle, dot, 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 whatever, circle, a y inverse here, and somehow bring those two together.
Could you do that, like prove that you can do that in group theory at any point? Or is
No, commutativity is not in general true in group theory. The basic example, I don't know if you would know this, function composition. You might have already come across in just algebra, f composed g is not the same thing as g composed f. But function composition is, with the right set of functions, it can be used as a group operation.
As long as you have the right domain, right?
Yeah, the domain you would use is called permutations,
I see.
which are types of functions. But, yeah, so function composition is not commutative. Function composition is definitely one of the things we use when we construct a group. And so, no, we can't assume that that operation is commutative, and in fact, it is not commutative. That would actually add structure. We can prove that if we added commutativity as an axiom, that it actually adds information. And how would we prove that? How do we prove that an axiom is independent of the other axioms? How do we prove it can't be proven from the other axioms? You come up with an interpretation where those axioms are true and your new one is false. And the interpretation we would use is function composition.
Okay, yeah.
Okay, anyway, so what is the z we're going to use? Now just looking at it, hopefully you can kind of just see it. Remember what the z is that we need right here?
It'll fit with theorem 8.
What is our z going to be so that when we circle it with y, we're left with x?
And what we just said.
Yeah, so what was it? Now just looking at it.
X circle.
I wouldn't try and remember. I'd look at it and see if you could just see it.
X circled inverse y.
Inverse y.
Yeah, okay. Just
Yeah,
looking at it,
so-
hopefully you could just have it scream out at you.
Right, so-
X circle inverse y is definitely what we want there, so it cancels out to x. Okay, so 2. Then, performing our calculation here, we're trying to prove that z circle y is in fact equal to x.
Isn't the let like a premise? Or is that just.
Let is the same thing as assume.
Right.
And we are basically making this as a conditional premise and showing it implies some conclusion. Is a common way that you're doing that.
Right, but there's no implication in this particular theorem.
All right, so in this case, we're just saying, this is basically doing universal specification.
Okay. I'm just.
So we're specifying two things out of our set, and then we're letting this equal that,
Right, so it's just.
and then showing that that makes, so this was our conditional premise, and we're showing that if this is true, then Oh no, this is going to be just naming it. Let's think. How might I do this using all of our things? We might kind of have to make a mess universally specifying with this.
Because like I see where you're coming from, but it just sounds like a premise, like a.
How would be the easiest way to say that? Let x, y, and g. So we're just grabbing two things out of g.
X, Y, and G.
Because this is just a relabeling, that doesn't matter. We never have to use z. We could just say, then this, circle that, is equal to that. So z is just a nicety here.
Well, actually no, because Z isn't in group theory before that, so it would just be like a.
I'm not sure how you would start out naming these things. I'm trying to think about it. So if we try writing this out all the way completely, what might I be able to say? For all x, y, there exists a z such that is the case. That is what we're trying to prove.
Could we use theorem 5 somehow?
Well, I think we're going to have to start out with axiom 1 somehow.
Okay. Yeah, no, that makes sense.
So I think we'd have to start out with universally specifying on axiom 1, somehow saying that
X circle parentheses Y circle Z.
x circle,
Y circle Z.
I don't even know if we want to start with that. Because we just want to say let x and y be just things out of our set. We don't even care that they're following any rules.
Right. Because they're in each. So maybe just have the first one be, well,
And we got to universally specify on something. I don't know how you would start those. You'd have to do something weird, like start with x, circle x inverse, circle x is equal to x circle x inverse, circle x.
okay.
Like something stupid to specify, get some element out of there out of x, do something similar for y. This is probably a really stupid way to do it. I just can't think of another way to do it off the top of my head. Something like that. And now I can say 3, let, I can say, just say z equals, now what was our z?
That was Y inverse plus, or circle X. Or,
X circle y inverse.
Oh yeah, the other way around.
And now that's just relabeling something. And then I can do the evaluation under that. I don't know how to grab my x and y out of there. That is weird. But this works. I mean, this says universally specify on that with some element x, universally specify on that with some element y.
Okay, and then number 3, is that still a premise, or is it just?
No, this is not a premise. This is just relabeling something.
Right.
We don't ever really need that z if we don't want, and we could go in our merry way. We could skip this line, and we could go to 4.
And we could write
say,
out X times.
right, we could say that z circle y is equal to,
X.
we'd have to write out all the rules, but ultimately we get that that is equal to x. And then we can existentially specify replacing that term with our z now. So then 5, using existential specification, I could then say, okay, so then there does exist some z, namely that piece, such that z circle y is equal to x.
Okay.
and then you can universally specify to get those two quantifiers. The weird part is doing this to like get my x and my y.
Yeah.
Like I'm not sure how you say, let x and y be in the set using our rules. But there's probably an obvious one to do it.
Yeah. Okay, that makes sense.
Might have been one of the theorems of logic that we skipped over. Oh, no, we do have that. So our theorems of logic are, we know if it's always the case, then there exist elements that make it the case. But that kind of still gets us to the same spot. Yeah, I don't know. This works. It's just ugly. And it's kind of confusing. Like, why are we, because we weren't even using associativity there. We were just grabbing elements by universally specifying. So it's weird, but it works.
Okay.
Logic doesn't care about weird.
Logic doesn't care about weird. No, it does not. Couldn't care less how we feel about it. It's just, did you follow the rules? If you followed the rules, you followed the rules. All right, so that finishes group theory. As much as we're going to go into it, there's more we can do, but we're not doing full-fledged group theory. So our last system that we're going to mess with before we move forward is arithmetic. And I think, can I see it all? I can see a line. Can I get both those lines? It's being really stubborn. Perfect distance. There it is. Okay. So that was it for group theory. Now, our next axiomatic system that we're going to talk about is arithmetic. The system that you are functioning with when you are in your basic algebra courses. And so, here's the axiomatic system for arithmetic. It almost has all the axioms on the real numbers. We're only missing one, which is called the completeness axiom. It's one you need for calculus, but it's not one that you typically tell young kids about. But it's one that lets you get irrational numbers. The completeness, well, maybe I'll say that after we talk about the theorems. So first off, let's just jump into it. So for arithmetic, what is it? We say, let that thing, we're going to call it times, and that thing, we're going to call it plus. So let those be operators on our set. That fancy R is going to be our domain. Everything, all our terms are going to be coming out there. So when I say let those be operations on there, what I mean is those take terms out there and spit out terms that are also in there. So let times and plus be operators on R, and let, we're going to call that less than, be a relation on R. What's the difference between an operator and a relation?
An operator is given two terms and it spits out another term, and a relation is given two terms and spits out true or false.
Perfect. Operators take terms, spit out terms. Relations take terms, spit out true or false. Relations in this special, a relation, predicates take terms, spit out true or false. A relation is a two-term predicate. It specifically takes two terms and spits out true or false. And times and plus here probably should have said let them be binary operators, meaning they also take two terms, just to be completely explicit. Okay, and so here are all your axioms for arithmetic. Here's all the axioms you use when you're doing your algebra. This is all of them. Let's go over what each of them says. We're going to notice that this is a much easier system to work in than group theory, because it gives us more tools to work with. So for all x and y, x plus y is equal to y plus x. Oh yay, we can swap terms. That's super useful. Similar, we call that the commutative property for plus, or the commutative property for addition. Next, same thing for multiplies. For all x and y, x times y is the same thing as y times x. Associativity for addition. For all x, y, and z, x plus y plus z is the same thing as x plus y, and then plus your z. So adding those together and then adding with that is the same thing as adding those together and adding with that. Next one says that multiplication is associative. So x times y times z is the same thing as x times y times z. Now what do you do when you get times and plus together, mixed up together? So we need some sort of rule that tells us how these things interact with each other, interplay with each other, and that's called the distributive property. So that tells us that x times y plus z is equal to x times y plus x times z. Now notice that these are binary operators, and so they always have to be taking in two numbers. Strictly speaking, if I write something like this, 1 plus 2 plus 3, strictly speaking, that's nonsense. And it either has to be 1 plus 2 happening first, so plus is taking those two numbers, and then this plus is taking the result of that and adding them together. So strictly speaking, we should have parentheses like that every time we write a plus. We might get lazy about that. Here's one that we're for sure going to get lazy about. When I do x times y plus z, that's the x times the y first, and the x times the z first, and then add the results together. Now, you and I are going to make an agreement right here, right now, that anytime we have both multiplication and addition showing up, we're always going to do the multiplication before the addition. And we are not going to draw those red parentheses, and it's going to save us a lot of hassle drawing parentheses. So we both understand that if I see something like 3 times 5 plus 2, that means 15 plus 2. That doesn't mean 3 times 7. Make sense?
Yeah.
So there's no rule that says that we can do that, because strictly speaking, you have to have the parentheses there, but we're lazy, and we don't want to always draw those parentheses there. So that's one agreement that we're going to have. We're always going to do our multiply before our addition. Next one is our identity element. Notice that this is identical to this. It's not an accident. There exists some identity element in R such that for all x, x plus that identity element is x. And notice that this is also identical to what that says, just with times and 1. There exists a 1 in our R such that for every x, x times 1 is equal to x. So we have an identity element for addition, and we have an identity element for multiplication. That's why 0 is referred to as the additive identity, and 1 is referred to as the multiplicative identity. Next one, this is our one that's a lot like your inverse element here. This is one that tells us there's negative numbers essentially. For all x, there exists some y such that when you add the results together it's 0. So if your x is 5, then the y is going to be negative 5. If your x was negative 13, your y would be positive 13. Or negative 13. We'll prove that negative 13 is in fact positive 13. Next one. So this one tells us when we have an additive inverse, every element has an additive inverse. Every element x has some additive inverse y such that their sum gives you additive identity. This one's almost the same. It says for every x, there exists a y such that their product gives you the multiplicative identity, with the one exception that your x cannot be 0. So every number has a multiplicative inverse except 0. That's what that's saying. And then these are our ones how to work with the less than relation. For all x and y, if x is less than y, then you can conclude that it is not the case that y is less than x. This next one, if x is less than y and y is less than z, then x is less than z. Remember what that property is called?
Transitive.
Transitive property. So if we have ARB and BRC, then we have ARC for any relation R. So yes, this is saying that the less than relation is transitive. Next one, for all x and y, if x and y are not the same number, then x must be less than y, or y must be less than x. Next one, if x is less than y, then x plus z is less than y plus z. So this tells you how to do your algebra when you have a less than symbol showing up in it. You can add the same thing to both sides. Next, for all x, y, and z, as long as z is a positive number, if you have x is less than y, then x times z is less than y times z. So if x is less than y, you can multiply a positive number to both sides, and the inequality is still true. Multiplying a negative number to both sides does not maintain the inequality. I know that 3 is less than 5. Let's multiply both sides by negative 2. I get negative 6 is less than negative 10, which is false. Negative 6 is greater than negative 10. Would you rather owe me $6 or $10?
So it reverses it.
Well, we'll prove that it reverses it, but we don't need that information in our axioms. Remember, your axioms are somehow trying to minimize the information you need to get everything you want out of the system.
Yeah.
And then finally, we have axiom 15 called the non-trivial axiom. which is that whatever that 1 is and whatever that 0 is, they are actually different things. They're not secretly the same thing.
Yeah, and it doesn't have any quantifiers on it because
Yeah, those are just constants. That constant and that constant, not the same.
no variables. Okay, yeah.
And that's it. These are all the rules you need to use in your algebra course.
Really?
All listed out. Okay, now let's think for a second. What are our primitive symbols or our undefined terms?
All the operators and
Yeah, plus and times,
0 and 1
0 and 1, and then the less than.
and less than.
Now notice so far, what symbols, what do we know is in our set R?
Real numbers, so that's
Based on our axioms, what do we know is in there?
just 0 and 1.
0 and 1, that's all we know is in R so far.
Okay. Yeah.
Right? And so, but we also know, for example, that 1 plus 1 is in R. Because we have a symbol from R, plus is a operation on R, and 1 is another symbol in R. So wherever 1 plus 1 is, it's also in R. Now how do I know that 1 plus 1 is something different from 0 or 1?
It's not.
Because they're not the same.
Well, we got to prove that. So let's start our first little proof here. Proof 1 plus 1 is in fact a different number from 1. Let's prove that.
Can you see it?
You can't see it?
Can it? I can't tell.
Yeah.
Okay.
Okay. No, that's good. Okay. So we're going to prove that this is the case. Now, what's a good way to try and prove that this is the case? Maybe a proof by contradiction. Assume 1 plus 1 is equal to 1 and get a contradiction. So assume, here's how we write this informally. We write by way of contradiction. That is so common that BWOC is very common abbreviation that shows up in mathematical proofs. So assume by way of contradiction that 1 plus 1 is equal to 1. Okay, if 1 plus 1 is equal to 1, what do we know? So we're going to have to use our axiom somehow. And our contradiction is that we're going to get 1 is equal to 0, so that's going to be our contradiction. So I kind of need to cancel out a 1 both sides, and then I get 1 is equal to 0, which is my contradiction. So looking back up here at axiom, hard to keep track of where they all are. I'll start using them rather than naming them explicitly. But this one says, for any number, there exists some y, such that when you sum it together, you get 0. So I'm now guaranteed then there exists some y such that 1 plus y is equal to 0. I'm guaranteed that by axiom, was it 8? Axiom 8 says for all x, 1 counts, there exists some y out there. We have no clue what that y is. Maybe it's 0, maybe it's 1, maybe it's something else. We don't know. But there is some y out there such that when you add together you get 0. Okay, so now what can I do with that y? Trying to manipulate this, ultimately to make this 1 is equal to 0.
You can add y to it.
Add y to both sides.
Yeah.
So then 1 plus y is equal to 1 plus y.
Right.
Now, using associativity, number 3
That's number
on addition,
3.
I can associate that with that. So this gives me that we can have 1 plus y is equal to 1 plus y. Okay? And what is 1 plus y? 0. So this gives me that 1 plus 0 is equal to 0. And what is 1 plus 0? How do we know? Oh, sorry, right here.
Oh.
for all x, x plus 0 is equal to x. Notice it's just like circling with E. Something circle E is just, 1. I wrote 0, sorry. Oh, no, because that was 0. Oh, sorry, that was a substitution. 1 plus 0, that's right here. 0 is from that. And now we were simplifying this. So then we get 1 is equal to 0. Contradiction. Back and forth arrows means contradiction. Why is that a contradiction? Axiom 15 guarantees me 1 is not 0. We just got 1 is 0. Contradiction. 4. Therefore, can't write it. Therefore, 1 plus 1 is not equal to 1. Oh, isn't that great to know? 1 plus 1 is in fact something different from 1. And we can do something different to show it's also not the same thing as 0.
Is it if we did not have axiom 15?
Then it is possible that if 1 is equal to 0, if they're actually the same thing, it's possible that our set of R is just a set containing 0. And all this works when you just plug in 0 for everything. So, the non-trivial axiom, the reason it has that name is because it makes sure that the system we're talking about isn't some trivial system. Some system with just one element in it that happens to satisfy these things. So now we know that 1 plus 1 is not 1. Let's pretend that we also did the proof that 1 plus 1 is not 0. So I know 1 plus 1 is in R. I know it's not 1. I know it's not 0. So I got to come up with a name for it. I'm just going to do like a weird squiggly and jolt out a line. That thing. Just made that symbol on the fly. And this is a symbol that is going to mean 1 plus 1. Whatever 1 plus 1 is, I now made up a symbol for it. 2. And we could go on and we can define 3 to then be defined to be 2 plus 1. Because now that 2 is for sure in R, and 1's for sure in R, 2 plus 1, whatever it is, has to be in R. And that's different from our other numbers. We would do some recursive definition to show that you guys don't know proof by induction, but it's not a hard proof style. It's just not one you're familiar with. To prove that adding 1 always gives you a different number. And the heart of it would be very similar to this. So we would get 3 then. We define that to be 2 plus 1. 4 we define to be 3 plus 1. And we go on our merry way. And so now we've defined, at least, what do we know is in R now so far? We know 0, 1, 2, 3, 4, 5. We have all the natural numbers so far in R. And we're guaranteed those.
About negative numbers. How do we know?
So far we don't have any negative numbers.
That's what I'm talking about, decimals.
We'll get there. We'll show how we have everything in the system. The only thing that this doesn't give us is irrational numbers. You need the completeness axiom for that. And now, since we've done all these, I'll tell you the completeness axiom, and it will mean nothing to you. What's the completeness axiom? It's that every set of real numbers bounded from above has a least upper bound. And that somehow gives you irrational numbers. Yeah, no reason for that to connect in your brain for half a second. We also use the completeness axiom in geometry. It's logically equivalent, but it's a little bit different. In geometry, we say any length you can construct has an associated number. Any segment you can construct has a length. And so, how do we get irrational numbers in geometry? Real easy, construct a square, that's 1 by 1. Now take its diagonal. That diagonal is the square root of 2, and that's how we can get the square root of 2. Since we can construct it, the completeness axiom in geometry tells us there's a number for it. It's logically equivalent to the completeness axiom in real analysis, but that's why they have the same name. But yeah, there's no reason for it to connect with your intuition how the completeness axiom gives us irrational numbers. That's what a field called real analysis is completely dedicated to, if we ever do real analysis. Real analysis would be starting with these and then just adding the completeness axiom. And then you just see what's true. And it turns out that gives you all of calculus. It's the interesting one, but the unintuitive one. Okay, but anyway, so now we got these numbers defined, right? Now we're going to do a crazy proof. Blow your mind. We're going to actually prove that 2 plus 2 is 4. We're going to do a full-blown proof of this now. And we now have all the infrastructure that we need to prove this. So how can we prove that? Well, what is 2 plus 2 equal to? What is 2 by definition?
1 plus 1.
1 plus 1.
1 plus 1. So I can replace one of those 2's with the 1 plus 1. I'll replace the right one. Huh?
Or both of them.
Or both of them, but we don't want that. So now I got is equal to 2 plus 1 plus 1. Now I can use associativity to shift my parentheses over here. So this is equal to 2 plus 1 plus 1. And what is 2 plus 1 by definition?
3.
3. So this is equal to 3 plus 1. And what is 3 plus 1 by definition?
4.
4. And boom, we just did it. We proved 2 plus 2 is 4. We proved something that probably the majority of people in math education don't know how to prove. 2 plus 2 is 4. Very sad state of affairs. Can't go into why modern education is such garbage. That will be a big tangent. But here's part of the reason. You could ask your algebra teacher, what's the definition of 4? You don't know what 4 is? Where are you, stupid? Yeah. And what is the definition of 4?
1 plus 3.
I'm going to be your annoying little brother. And what's the definition of 3?
That's 1.
And what's the definition of 2? And what's the definition of 1? Bad question. It's a primitive. It's an undefined term. You are showing your ignorance by asking that question. You're showing that you have no understanding of the foundations of arithmetic when you ask for a definition of 1. Bad question. Definition of 0. Bad question. Definition of plus, times, less than. Bad question. Definition of less than or equals. Okay, that's defined. And we can define that. So, not everything is defined. The axioms give meaning to our undefined terms. Okay, so do we have time for just one theorem?
Wow, time flew.
Depends on it.
Yeah, it did fly. Let's do one theorem just so that we touched it, you know? Theorem, our first theorem is for all x and y, x plus y equal x implies y is 0. Okay, so theorem 1, for all x and y, if x plus y is equal to x, that gives me that y is equal to 0. And you'll notice that this is exactly what we already proved over, it's this exact thing, just in arithmetic now. We don't need as much work to build up to it because our axioms give us more things to work with. Okay, so let's get started. Assume the antecedent. So let x plus y equal x. Now what do we do? I somehow need to cancel out the x on both sides. How do I cancel out my x when we're talking about sums?
Subtract it.
Add the inverse. Subtract? What do you mean subtract? We haven't defined that yet. We will define subtraction, but we're not there yet. But we know how to add an inverse, so I'm guaranteed that there is an inverse by this. For every x, there exists a y such that their sum is 0. So we're saying y is the additive inverse of x.
Okay.
It's the thing that when you add to x, you get additive identity. That's why it's an additive inverse.
But y in this case is not the inverse.
Y in this case is a different.
Oh wait, it is the inverse.
So, well, no,
No, it's
y in
not.
this case is 0.
It's-
So then there exists, we can call the symbol whatever we want. I'll say w. Then there exists w, such that x plus w is equal to 0. How am I guaranteed that? I'm guaranteed that by axiom A. Axiom A says every number has an additive inverse. Right? So 3. So now I'm going to add that w to both sides. So then, w plus x plus y is equal to w plus x. Have to add it in the same spot. This is using, clear back to logic. Which one did we use? Since I added it on the left-hand side, I'm using Theorem B there from logic. Right? Okay, now what? I know x plus w equals 0. How annoying, I have w plus x. Who cares? Addition is commutative. Swap them around. Ah, we love arithmetic. Everything's so nice. And technically I should have had parentheses right there. So I'll move the parentheses and swap things around. We'll do some associativity and commutativity all in one go. So I'll call this x plus w plus y is equal to x plus w. Using both A1 and A3 right there. Associativity and commutativity. And now I know x plus w is 0. So 0 plus y is equal to 0. Or in other words, y is equal to 0. We won't bother swapping and doing it. So we did it. So I know that if x plus y equals x, then y must have been 0. Good? Alright, so there's a taste. And we'll do arithmetic next time. Kind of pushing arithmetic in case we decide to do real analysis after logic. It's a very natural thing to go into next. And so, just in case, arithmetic, it's a good one to cover. Plus, you've already have so much experience with arithmetic. It's nice to now know that you can prove 2 plus 2 is 4. Doesn't that feel good?
That does. I actually really love having the axioms for this because it feels like arithmetic is always just like that.
Yeah, it's always like, because you can. Don't you feel like you can?
Yeah, hasn't worked in every single scenario that you've tried it.
Yeah.
Yeah.
It
Very
just works. It's just how it is.
bad reasoning. It's terrible how arithmetic is taught now, and how most geometry is taught. You guys are getting geometry
No one
from me,
teaches
but
this like this.
huh?
No one teaches things on a proof.
And it
No
used
one
to be the
proved-
way that everyone did it,
Not one time.
and the world just went nuts.
I ever been taught what a proof is until you showed up.
Yeah.
Yeah, I know the feeling. Turns out you and I went to very similar schools.
Yeah.
Okay. Anything else you want recorded?
I was gonna ask what the will you remind me what the textbook is for the course?
It's posted on the Facebook page.
Okay.
It's just like there's a files tab. I can show you really quick after class where it is exactly on the page. Just to give you a sense of where we're going next, we only really have one more piece of logic to cover, and that's a theory of definition. So that's the only thing we haven't quite touched yet, is how exactly we make sure something's well defined. So that's the only piece of logic we have left. Other than that, we're just going to do examples. We'll do arithmetic, then we'll get into theory of definition, and then we'll get into most likely set theory and call it there, depending on where you guys want to go next. Okay, anything else? Cool.